Welcome to Brain Vision.
Okay, for question A, since we know there's no work and there's only negligible amount of changes in kinetic energy and potential energy, so therefore we can set out such energy balance equation here, which is E dot equal to E dot L. If we expand it, we have Q dot plus M dot 1 times H1 plus M dot 2 times H2 is equal to M dot 1 plus M dot 2 times H3. Q dot here is the heat transfer from the surroundings. And we know M dot 1 is the mass flow rate for the first ideal gas. H1 is the enthalpy for the first ideal gas. And M dot 2 here is the mass flow rate for the second ideal gas. H2 is the enthalpy for the second ideal gas. And H3 here is the enthalpy for the mixture. So now we can do some arrangement here. So we know that H3 can be equal to M dot 1 times H1 plus M dot 2 times H2 plus Q dot over M dot 1 plus M dot 2. And we know H3, which is the enthalpy for the mixture, can be equal to specific heat for the mixture times the final temperature of the mixture, which is T3. So therefore we have CpT3 is equal to M1 dot H1 plus M2 dot H2 plus Q dot over M1 dot plus M2 dot. And since it was saying that assume the gas has constant specific heat, so therefore the specific heat for all the ideal gas here should be the same. So therefore we can express H1 as Cp times T1, and T1 is the temperature for the first ideal gas, and H2 can be expressed as Cp times T2. Okay, if we do some arrangement, we have CpT3 is equal to Cp times M1 T1 plus M2 dot T2 and M plus Q dot over M1 dot plus M2 dot. So therefore we can move Cp to the right side. We'll have T3 is just simply equal to Cp times M1 dot T1 plus M2 dot T2 plus Q dot over Cp times M1 dot plus M2 dot. So for the next question, while we know the mass flow rate for the mixture can be equal to the volume flow rates of the mixture divided by the specific volume for the mixture, which is capital V3 dot over lowercase v3 here. So we have V3 dot is equal to M3 times V3. According to ideal gas law, we have PV is equal to RT. P is the pressure, V here is the specific volume, and RT, R is the gas constant, T is the temperature. So we have V is equal to RT over P. So therefore we have V3 is equal to RT3 over P3. So we have the volume flow rates for the mixture is equal to M3 dot times RT3 over P3. And remember from the previous question, we know that T3 is equal to Cp times M1 dot T1 plus M2 dot T2, and then plus Q dot over Cp times M1 dot plus M2 dot. And also we know that the mass flow rate for mixture with M3 dot here should be equal to the sum of the mass flow rate of the two ideal gas. Okay, so now we can plug in back to the equation. So we have a new equation for the volume flow rate of the mixture, which is equal to let me see, R over P3 and then times M3, which is M1 dot plus M2 dot, and then times T3, which is Cp times M1 dot T1 plus M2 dot T2, and then plus Q dot over Cp times M1 dot plus M2 dot. As you can tell, M1 dot plus M2 dot can be cancelled out, and this will give us V3 dot is equal to R times P3, and then multiplied by Cp times M1 dot T1 plus M2 dot T2 over Cp and plus Q dot. And as you can tell, this part can be expressed something like this, which is I will show you. So V3 dot can be equal to R over P3 times Cp times M1 dot T1 and then plus M2 dot T2 over Cp plus Q dot over Cp. And as you can tell, Cp here can be cancelled out. So this will give us V3 dot is equal to R over P3 times M1 dot T1 plus M2 dot T2 and then plus Q dot over Cp. And also, we know in this question, we're saying that the pressure is constant. Okay, so which means that P1, which is the pressure for the first ideal gas, should be equal to the pressure for the second ideal gas, which is P2, and then equal to the pressure for mixture, which is P3. So therefore, we can use P3 substitute for each pressure here. So we have V3 dot is equal to, you know what, let me use this is a P here, okay? So you look more organized. So we have R over P times M1 dot T1 plus M2 dot T2 and then plus Q dot over Cp. And then we can distribute to R over P. So we have V3 dot is equal to M1 dot RT1 over P plus M2 dot RT2 over P. And then plus RQ dot over P times Cp. As you can tell, P here can be expressed as P1 and P2. Okay? And remember the volume flow rates is equal to the mass flow rates times the gas constant times the temperature over pressure, because RT over P is equal to the specific volume. So now we can use such formula here and then plugging back to the equation. So we'll have V3 dot is actually just simply equal to V1 dot plus V2 dot, and then plus RQ over P3 times Cp. Oop. Because remember P is equal to P3. Or you can just leave P here as P. It's fine, okay? So you know what, let's forget about this. So just P over P times Cp. So this is the expression for the V3 dot, which is the volume flow rate for the mixture. So now for the special case, which is the third question. So you were saying that it's a adiabetic mixing, which means that there's no heat exchange with the surroundings. Okay. So therefore, the rate of heat transfer in this case should be equal to 0. So we have the equation for V3 dot is just simply equal to V1 dot plus V2 dot, and then plus R times 0 over PCP, which is equal to V1 dot plus V2 dot. Okay, so I have V3 dot is equal to V1 dot plus V2 dot if it's adiabatic mixing. And these are the answers for this question.